everyone. Welcome to Pivot 2023 on geothermal research. My name is Yitian Xiao. I'm the Chief Research Scientist with Sinopec. It is my honor to serve as the moderator of this special Pivot session on geothermal research in China. We have three invited panelists or speakers and who will give the presentation. So let me first introduce our next speaker, Dr. Feng Jianyun from the Exploration and Production Research Institute of Sinopec. His presentation is Exploration Potential of Geothermal Resources in Eastern China. Dr. Feng, welcome and please give your presentation. Thank you.
Okay, thank you, Dr. Xiao. Hello, everyone. I am Jianyun Feng from Sinopec. I have been working in the field of geothermal for nearly 10 years since 2014. It's my pleasure to share our latest studies on the exploration potential of geothermal resources in Eastern China. By the end of 2021, China's geothermal heating and cooling capacity reached very large square meters, and the annual utilization capacity of hot springs is 6,665 megawatts. All of this, all infer that China's geothermal industry has entered a stage of rapid development. My presentation will have four parts, starting with geothermal background. From this picture, we can see that China has been divided into two parts, the west and the eastern. It's divided by the Huhuanyun land. This land is a very interesting land, and into the east of this land, the region accounts for 36% of the total land area of China, and is dominated by plains, hills, karst, and Danxia landform. It also has a high population density, accounting for 66% of the total population of China, as well as a developed economy and a huge demand for energy. First, the northeast China lithosphere block. This block is very large, and the geotectonic setting in Eastern China consists of the near east-west trading eastern segment of the Central Asia Erotic Belt, the North China plate, and the South China plate. The region is superimposed by geology and structures belonging to three major global tectonic domains. And the lithosphere structure of the North China is characterized by a thin, low density and crust and mantle, and high conductivity zones exist at depths of 10 kilometers in the upper crust and 30 to 40 kilometers in the lower crust, which is believed to the geothermal anomaly is attributed to this. And next is North China lithospheric block. This block is about 10 kilometers thick and is underlain by 2 to 8 kilometers thick crust mantle transfer layers, and they are buried at a depth of 72 to 103 kilometers and might be the bottom boundaries of the lithospheric mantle. The next is South China lithospheric block. This is in the southeast of China. The lithospheric mantle also varies greatly in thickness. It's very different from the North China and the northeast China. The addition to the absence of a high conductivity zone in the crust suggests that the western lithosphere of SCLB is characterized by cold and thick rigid blocks which have a thin, low density crust and a thick, high density mantle. The second of my presentation is distribution of geothermal resources. For the northeast China, porous sandstone and geothermal system is developed well. In this area, the most important is the Songliao Basin, which in this basin, the heat source is mantle-derived, and the water source is infiltrated meteoric water, and the channel is lithospheric and crust faults. Because this is oil field, also this have very well developed reservoirs for oil. So the geothermal reservoir is Cretaceous sandstones, and the Kewen rock is Cretaceous mudstones and argillaceous rocks, which is graben, like in riptide. The next is in North China. Here are two silt reservoirs. It's porous and cast compound geothermal systems. The heat source is also from the mantle, and the channel is lithospheric and crustal faults along the Taihang Mountains. And the geothermal reservoir are two silt like the Newgen sandstones, mean that the Guantao and the Minghuazhen formation, and the Mesoproterozoic carbonate rocks like the Jixian Wumishan formation, and the Kewen rock is quaternary deposits. The last is the porous sandstone and the fissured granite geothermal systems in southeast. In southeast China, its heat source is mantle and crust derived, which the crust is mainly from the granite radioactivity, and the channel is lithospheric and crustal faults. And geothermal reservoirs are two silt like the Paleogene sandstones and the Permian to Triassic granitic rocks, and the Kewen rocks is quaternary and Newgen deposits. The three parts of my presentation is geothermal potential. First, in this map, we can see in the geothermal anomal field is in east is very developed in the large basins, and the project for the exploration and the utilization of geothermal is most concentrated in these areas. In the northeast China, the Cretaceous sandstones in the North Songliao Basin have abundant geothermal resources at a depth of 2,000 to 4,000 meters with great potential for exploration and utilization. So it's necessary to strengthen geothermal heating for human habitability for agriculture, like planting and breeding, and for the development and application of mineral water. In North China, geothermal potential is also very good. There are three major geothermal reservoirs, like the karst reservoirs of Jixian Wumishan formation of Mesoproterozoic, and the karst reservoirs of Ordovician shore, and the sandstone reservoirs of Newgen, Guantao, and Minghuazhen formation at depths of 1,000 to 4,000 meters. This area, the area of Hebei, Henan, Shanxi, Shandong, Beijing, and Tianjin have geothermal resources of a large, very big, and the recoverable of heat is also very good. It should mainly be used for geothermal heating, planting, and breeding, as well as in expanded fields of applications such as geothermal power generation and industrial utilization in areas with appropriate conditions. The last is in southeast China. The geothermal potential is also very good. The moderate to high temperature geothermal resources and HDR, this means hot dry rock, resources enriched in pre-Cenozoic granite geothermal reservoirs such as Maichen and Fushan sites in the Beibuwan Basin, and the Baoyue site and Yuezhong depressions in the Sanshui Basin. High temperature geothermal resources can generate considerable amount of power, as can be low to moderate temperature geothermal resources, indicating great potential for exploitation and utilization. Geothermal heating in the winter and geothermal cooling in the summer are applicable in the Yangtze River basin zone, while geothermal cooling is applicable to the zone in the south of the Nanning Mountains. So the last is the conclusions. East China is a superimposed region in the Pacific Ocean, Paleo-Asian, Circum-Pacific, and Tertiary tectonic domains. Its crust mantle structure presents a spectral flyover pattern, while its shallow surface has alternate basins and origins, and well-spaced uplifts and depressions. And current technical conditions favor the adoption of direct utilization over large-scale geothermal power generation for the exploration and utilization of geothermal resources. That's my presentation. That's all. Thank you very much. Okay, Dr. Xiao.
Okay, everyone. Now it's my pleasure to introduce our second speaker, Dr. Xiaobo from CEEC. His presentation is on thermodynamics of underground thermal energy storage. Dr. Wu, welcome.
Hello, everyone. I'm Xiaobo from the industry and work as a principal scientist of the CEEC Geothermal. My majoring is the thermal energy science, and today I will give the presentation of the thermodynamics of underground thermal energy storages. First, I will introduce what about the underground thermal energy storage. And there are three kinds of the thermal energy storages. And one is the aquifer thermal energy storages, and the second is the borehole thermal energy storage, and the third is the Kewen thermal energy storages. Well, as for the larger scale application of the underground thermal energy storage, was the first realized with the 80s in Shanghai in 1960s for the practice of the land subsidence control. And later, this technology was further developed in the Netherlands in 1990s. At this moment, well, the research and the development of the UTIS is implemented under the IEA ECES program, and which was initially initiated by the group of geologists in 1979. But still, this technology viewed as a highly innovative technology for the most country. And then when we're talking about the thermal energy storage, first we need to focus on the energy conservation of the shallow ground. You know, the heat flow from the Earth is very small, and something on the average is about 33 milliwatts per square, which is almost negligible for the application point of view. And some people also question maybe the energy is from the thermal energy is from the surface, but well, this part is also very small, about 15 watts per square meters. And from heating and cooling point of view, this is also not big enough. And on the average, on the annual averages, this value is 0. And for the shallow part of the Earth, the temperature of the ground is on the average of the temperature of the atmosphere. So it's belong to the low entropy energy. And although this volume is very large, but it's not suitable for the long distance transportation, and also for the exploration, it's also very limited. So we think the role of the shallow ground is seasonal thermal energy storage, or small scale or balanced heat pump. The role of the shallow geothermal is a storage. And then we were talking about how to use the underground in thermal energy or in a high efficient way. We will prefer to use the stored heat and cold in a more efficient way, which the heat pump will not be used, and which we call it the passive heating or cooling, or sometimes we say the free heating and cooling. And during the storage process, we want to store the heat or the cold with less temperature loss. How to do that? Thermal stratification design, and which is similar like what we design for the water tank thermal energy storages. So in such a way, the heat or the cold quality can be maintained at a large extent. Also, in such a way of the heat transfer, and it is also very efficient. So on the right side of the picture, you can show the very efficient storage of the heat and the cold. So we will go back to the underground thermal energy storage. If you look at this, we also, when we design of the underground thermal energy storage, we designed on the cold zone and the warm zone. For the 80s, it's more clear. We use a cold well and a warm well. And during the summer, we extract the cold water from the aquifer, and then we will cool the buildings, and then the water will become hot. And this hot groundwater will be rejected into the hot well. And in the winter, it will be vice versa. So for 80s, it's very clear. And for the 80s, we also divide the cold zone and the warm zone. And of course, for the Kewen thermal energy storage, this is very similar to the water tank thermal energy storage. So in such a way, it will be more efficient. For the heating and cooling with the thermal energy storage, we need to design which kind of the heat we need to store, and in which kind of the what the temperature level we can get from the energy storage, and which is very important for our free heating and cooling, or the passive heating and cooling. So design is very important. We need the tools, and we develop the tools for the aquifer thermal energy storages, and which can be used for us to well location design, thermal influence, and also very important, underground thermal balance. So on the right side, this is a thermal response temperature from the ground, which we can use for the design of the whole energy system. Of course, for the extraction of the groundwater, and then at this moment, the groundwater should be re-injection 100%. So well quality and the well design is crucial to ensure the 100% of the groundwater be re-injected. And then we realize the high quality well for the all kind of geologies. And also, the groundwater system is also very important. It should be airtight, and then the 100% re-injections. Of course, control system, monitoring system is also very, very, very important. So the second is I would like to talk about the BTS, borehole thermal energy storage, because for the rest of the world, the BTS is still not popular. Why? Because it's too expensive. However, in China, the BTS price is already low because due to the lot of the underground thermal energy and ground source heat pump project has been realized in China. And we want to upgrade this system to the UTIS. And first we make the kind of the model. And on the right top, this is for the small scale BTs. And on the left side, and we use the modular BTs design with a different temperature zone. And this will be used for the larger scale BTs. And then you can also see we also developed the model for the thermal response of the temperatures, which is important for the climate, for the total system. Of course, the drilling quality of the borehole heat exchanger also very important. But well, underground thermal energy storages is still one part of our energy system. So we need to implement the system to the whole energy system. And so in order we can realize a passive heating and cooling with high energy efficiency. And also we need a renewable heating and cooling sources. And in order to realize, and also we need to choose the right climate system and for our system. So this is a renewable heating and cooling source. We can use the heat and cold from air, from water, and from solar. And also we can recover the heat and cold from the industry, which also include the heat pump. And the climate system also have impact on the energy efficiency of the whole system. So if we, for example, if we use the heat pump and for the floor heating, and its energy efficiency is very high. But if you use the radiator, and the energy efficiency is low. So I think at this moment, low temperature heating is also important for the energy efficiency. UTIS is still not popular all over the world, but in some countries it's already widely applied. And especially for the Netherlands, they are already realized more than 3,000 projects. And in some people also call the UTIS is a kind of the upgraded ground source heat pump technology, or the next generation shallow geothermal. So far, we have realized about 20 projects in China, and this is some example of our project. This is a Sino-Germany vocational school, which with 2,400 borehole heat exchangers and with a depth of 120 meters. And this project has been operated in the 2020. And this is the project, our project for residential buildings, and the project with the 1080s well, and the project also has been started in the 2020. And this is our project for the horticulture, and this is our third 80s project for the greenhouse in Shanghai. Is a high-tech greenhouse. And we use the passive cooling with active heating for the greenhouse temperature control and the humidity control. Usually, we're willing to cooperate with the international communities. So we already introduced some of the high-tech drilling technologies, and also we adapt to the local situations. And also we support the Japanese counterpart for their 80s project. This at the middle of the picture, we cooperate with the Japanese company Mitsubishi Heavy Industry for their realization of the 80s. And we also cooperate with the Dutch Business Consortium and to develop our application for the various industry. So this is the end of my presentation. Thank you for your attention.
Hello, everyone. Now it's my pleasure to introduce the third speaker of today's session, Dr. Kewen. Dr. Li is from China University of Geosciences, Beijing. His presentation is on a machine learning methodology for predicting geothermal heat flow in the Bohai Bay Basin, China. Okay, Dr. Li, welcome to today's session.
Okay, good. Thank you very much, Dr. Xiao. My name is Kewen Li, and these are my co-authors. I would like to show you the amazing function of machine learning methodology for predicting geothermal heat flow. As you know, geothermal energy is clean and renewable, which is very important to reduce the carbon emission. Geothermal heat flow is one of the most important parameters in exploring geothermal energy. However, the measurement data points of the heat flow are very few, and so we usually need to do the prediction, which the regular routine method we use is interpolation methods. However, this methodology doesn't have very high accuracy, and in many cases it gives very poor prediction results. So, for example, this is the Bohai Bay area. We have some measured data points of the heat flow, but it's only in some parts, not the distributed evening. So we need to do some prediction. So today I would like to show you how to improve the prediction of geothermal heat flow. And the machine learning methodology has presented or demonstrated some advantages to do the prediction. For example, here, the heat flow prediction in Greenland showed very good promise. And today I will show you some of our prediction results in Bohai Bay area in China. Before that, I would show you some advantages of the machine learning methodology compared with the traditional prediction process. One of the advantages is no need to predetermine analytical equations. And the second one is machine learning methodology has could fully consider the combined effect of multiple geological and geophysics features, we just say GGF. And another one is the relatively high accuracy. And also what I like is the ability to keep improving the function or ability of the prediction with the data addition. And we used about 249 heat flow data from the Bohai Bay, which are measured. So you can see it's kind of a normal distribution. And this is not the important part. And I would like to show you, we consider the 8 GGF or geological geophysical features to do the prediction. And by the way, we use the 60% of the measured data for the training purpose and 40% for the validation. So you can see which is the red dots, and the training dates are in blue color. And you can see for each GGF, there is no good relationship between, the GHF, which represent geothermal heat flow, with the single geological feature. So the same thing for the other four. So you can see if we use the traditional method, maybe we'll have trouble to get high accuracy of the prediction. So how we can do with the machine learning methodology. And before I show you the results by the machine learning methodology, I will show you the traditional method, which we use the Kewen and the inverse distance weighting interpolation method. And you can see here, the R square value has only 34 or 37%, which is not bad, but well, the higher the better, right? For the other two parameters, the regression parameter, you don't have to pay much attention here. So you just look at the R square value. So remember here is like 35% or so. And if you look at the results by machine learning methodology, it's not very high for the GLM. By the way, for machine learning methodology, we have many models we could use. Here we use the four models I will show you later. One is GLM, one is GBRT. GBRT represents the gradient boosted regression tree. So for GLM, the R square value is 66%. It's not very high, pretty much the same as the traditional interpolation method, but the GBRT model could give a significant high, that's 47% of R square value. How about the other two? SVM, we could get 55%. That's pretty good, right? And for DNN, which if you are not familiar with machine learning, which represent the deep neural network method model. And both of these two methods could give like over 50% R square value, which is pretty good or much better than the traditional method, right? We use the same data points. So that's like 60% higher than the traditional method. And we are not satisfied with this. And then we combine the two DNN and SVM model, we call a hybrid model. And then you can see we could get like the value of R squared 62%, which is very good. And this is I can show you the hybrid model of machine learning methodology is much better than the traditional Kewen method. But how about the real situation? And to do this, we made the new map of the Bohai Bay area, and you can see the heat flow. This is the low area, and this is the high heat flow areas, which is consistent with our known measurements of, for example, heat flow data measurements and other data, and also the geological features. So you can see here, this is our new predicted heat flow map of Bohai Bay in China. And this is the gravity anomaly. You can see they are consistent with each other pretty good. And the same for the Moho depth. And you can see if you, okay, the before maps are the results predicted by the machine learning methodology. This picture shows the results of heat flow predicted by traditional Kewen method. And you can see here, the heat flow map predicted by traditional method could not, are not consistent with the geological features, for example, gravity anomaly, and also the geothermal gradient, which are not consistent with each other. And so here you can also this is a predicted heat flow map using the machine learning method, but you can see here, once again, the machine learning method, the predicted heat flow map are consistent with most of the geothermal geological features. For example, the geothermal gradient, you can see very clearly. So, because of the time limit, I just show you some of the results, but in conclusion, machine learning methodology outperformed the traditional interpolation methodology in predicting heat flow in the Bohai Basin in China. And if you want to look at the detail or specific value of R square, our machine learning methodology could get the R square value of 62% over the 37% of the traditional methodology. And we also generated the new geothermal heat flow map in Bohai Bay. And I showed you that the new geothermal heat flow map are consistent with most of the geological and geophysical features. So the takeaway point is that the methodology is much better than the traditional method. And thank you very much. Thank you very much for your time. If you have some questions, any questions, let me know. That concludes my talk. Thank you very much again.
Okay, Dr. Li, thank you for your presentation. Now we just completed our 3 presentations, and we're going to move on to Q&A session. So as the moderator, I have gathered a few questions from the audience. So let me start with a question for Dr. Feng. Okay, Dr. Feng,
Okay.
Here is a question from the audience. Have the granite in southern China been considered as potential targets for enhanced geothermal systems?
Okay, thank you, Dr. Xiao. It's a very interesting and very good questions. And as we studied in the Southeast China, we found that almost all the hot springs are developed in the granite of the Permian to Triassic granites. So we think the granite in the Southeast China have very potential target. It's a very good potential target for the enhanced geothermal systems. Thank you.
Okay, that's a very good answer. Here is another question, Dr. Feng. Could you elaborate on the depositional environment of the Cretaceous sandstone targets in the northern Songliao Basin? So here is a question about the depositional environment of the Songliao Basin. Please.
Okay, thank you. We studied that in the Songliao Basin, the target reservoir is Cretaceous sandstones, and the sandstones is mostly like very fine and the made fine to sandstones, and it's formed in a continental environment. So it's like a lake in the Cretaceous. So we thought this is very important for the reservoir to form and to give a very good porosity and permeability for its collecting the geothermal waters. Thank you.
Okay, thank you, Dr. Feng. We may have additional questions coming back to you, but let me move on to our second speaker, Dr. Wu Xiaobo. Here is a question from the audience. Dr. Wu, is there a comprehensive map encompassing all current and upcoming geothermal projects across China? I guess this is probably too broad of a question. So maybe if we narrow down a little bit, is there a comprehensive map that summarizes all geothermal storage project across China? Dr. Wu?
This is a very good questions. And well, I think for the shallow part of the Earth, there are already a lot of information from the geology survey, which we can use as our project, but it is still a kind of the indication for the modeling and for the drilling design. We still need more information. So due to the geology uncertainty, we have to do the test drilling for our project. So I think for the uncertainty, every project is different. We need to do the test drilling. Yeah, that's my answer.
A follow-up question, Dr. Wu. So I guess your approach is based on some fundamental thermodynamics theory and calculations, which is sort of on the provide a fundamental and useful static picture, but considering some of the storage has moving parts, right? So it's a dynamic system. What are some of the other tools that can be used to address those sort of questions, geological and engineering aspect of the storage, please?
Well, for our project, we usually, before the project, we needed to do a kind of the test drilling, and also we needed to check if the groundwater is flow, and which may influence the project. And then after we finishing the project, and then we needed to install the control and the monitoring system to check if the modeling is accurate enough. For example, when we make the ATIS in Shanghai, and we validate our modeling with a historical ATIS field in Shanghai, and which was a 4-well and 438 observation hole, and the result indicate our modeling is quite accurate, especially from the thermal point of view.
All right, thank you, Dr. Wu. Now here are a couple questions for Dr. Li. The first question is, has there been any consideration of the integration of data from producing oil and gas asset into the machine learning model for the purpose of converting them into geothermal heat-producing wells? Dr. Li?
Okay, thank you. I think this is a good idea, but the answer in short is we haven't done so. Of course, a lot of data from oil and gas industry could be used in geothermal industry in general. For example, the heterogeneity of faults, or a lot of data like well logging, some other measured data are very useful in geothermal industry, as I said, in general. But talk about the machine learning methodology, I think a lot of data from oil and gas could be used in the machine learning data set. But in the talk I showed, we haven't done so because we use mostly the geothermal heat flow measured data. Of course, we collected some of the geological data, such as the Moho depth by WeChat, which is not very used. I mean, it's not very often used in oil and gas industry. But once again, I think it's a good idea when we do this in the future.
Okay, thank you, Dr. Li. Here is another question. I know a lot of folks are interested in the machine learning, artificial intelligence technology, and I believe your work is perhaps one of the early studies using this technology. Have you considered running a workshop or hosting a hackathon where teams of students or interested in the data geothermal professionals can come and compete or learn to sort of optimize the machine learning technology?
Yeah, once again, this is a good idea, but we haven't done yet. I know in oil and gas industry, they have some event like this. For example, SP organize a lot of this kind of student competition. For the machine learning method, we could do the similar thing in China or worldwide for sure. Yeah, but maybe we could do this in the next conference to organize some students and some research groups to do so. Yeah, that's a wonderful idea.
Yeah, I know that they do organize the sort of short course hackathon, in some other conferences like APG, SPE, all that. So perhaps I will talk to the organizers for Pivot 2024 or the Heidelberg conference to be scheduled in 2024. See if they have time slots to organize a short course or hackathon for half a day for people to talk about this technology. So hopefully you will be interested.
Can I add one more thing?
Yeah, please.
Actually, I remember in terms of the workshop, the World Geothermal Congress, WGC, will be held next month in Beijing. And I actually was invited to give a talk or lectures for the workshop. Yeah, it's a big workshop, but I will talk about the machine learning methodology. Yeah, we have a lot of students from worldwide. Yeah, so that's a workshop, not a competition. Yeah.
Okay. All right. Yeah. Great.
Just let you know.
Okay. Yeah. Well, thank you very much. We have a bit of time left. So instead of asking you guys questions, I will offer each of you 2 minutes to sort of talk about, your current work, or perhaps more so your future plan, so to give your audience as to what a geothermal research is going to shape from your angle, from your perspective, going forward. Okay, so Dr. Feng, I will start with you. So your future plan, your future research plan and outlook.
Okay, we are now studied the geothermal in almost the whole China, but we are most focused on the selection good or well site for EGS or some hydrothermal, geothermal, like the Forge in America. This is very interesting, and in China, we all know it's a very complex the geology background. So it's very difficult to find a good or a well or ideal site for EGS for all the hydrothermal, geothermal experiments. So we plan to make like we are now some programs like in the Eastern China and the East South China. We are to find good or with our geothermal production. Like we are planning to drill a borehole in the Haikou city. This will start maybe in the end of this month. Okay, and this hole is very important for China's geothermal because it's the first scientific geothermal hole for it's more than 5,000 depths, 5,000 meters depths. So it's very, very important and is significant for our China's geothermal development. And besides this, we are now will do something work on the new energy, like some the solar and like the wind energy. It's how to combine this new energy to geothermal. This is the next plan. Okay, that's all. Thank you.
Thank you, Dr. Feng. I know that as the largest oil and gas company in China and perhaps in the world, Sinopec has taken very active steps to explore those new energies, right? You mentioned geothermal, solar, wind, hydrogen, all that. So very excited to hear your presentation. I'm sure you guys will do a lot of interesting project going forward. So thank you, Dr. Feng. Okay.
Okay, thank you.
And Dr. Wu, would you offer a brief sort of a summary of your perspective and outlook?
Yes, and I think from my point of view, I hope, because I'm energy expert, geothermal energy, I'm a thermal energy expert. So I wish that the geothermal energy should be energy efficient. That's one. Second is should be cost effective, and in such a way everybody can use it. And the second aspect is we should also take care about the geo environment. That's also very important to reach the social benefit and for the sustainable development of the geothermal. Thank you.
Okay, very good perspective. Yeah, efficient, cost effective, right? That's the key. So thank you so much. Last but not least, Dr. Li, would you offer some outlook and comment?
Sure. The talk I presented today actually is the prediction of geothermal heat flow in Bohai Bay. Actually, this is a big area, but compared to the entire China, it's a very small area. So our next step is to do the prediction for the geothermal heat flow in the whole China. So because in many areas of China, we haven't measured the geothermal heat flow, so we need to do the prediction. And we found that actually it's not very good if we just use the traditional method. And we found actually, you can see from my presentation today, machine learning methodology is very powerful. So that's one of our plan in the near future to do the prediction in China for the geothermal heat flow. Because, you know, as I mentioned before, heat flow is one of the most important parameters in exploring geothermal energy, and also in the development of the geothermal energy. We need it, especially in the areas we haven't measured the data a lot. So this is one thing. And our group has two actually research direction. One is the prediction of heat flow, and another actually is on the application side. I don't know if I could do it. I should say it or not. Just in short, it's the application of thermoelectric generate for power generation using the thermal energy, and it's very totally different technology compared to the turbine technology. So if you are interested in, you can Google my name. Yeah, so and then thermoelectric generate, and you can find a lot of publications. Thank you, Dr. Xiao, and thank you everybody for listening our talk. Thank you.
Okay, thank you, Dr. Li. That gets to the end of our session. So on behalf of Pivot 2023, I want to thank each of you for your nice presentation and for your Q&A session, and also for offering your personal perspective and outlook of some of the research programs. I'm sure that the audience will appreciate your talk, your knowledge, and wisdom. I hope we'll hear some of your exciting and interesting talk in future events. Thank you so much. Okay, that concludes today's session. Thank you. And thank you for the audience for your attention.